Alright, so in this video we're going to look at starting in. Okay, in this video we're going to look at another application of calculus, and that is looking at rates of change. So some real life examples of this might be when temperature varies continuously, so looking at the rate of temperature change throughout a day. Might be looking at the height of a tree. How does that vary as it grows? Might be prices of stocks and shares with each day's trading. Might be that. Might be flow rate of a tank as it's emptying water. So there's lots of different rates of change that get used in the real world. So this does definitely have real world applications. So what I've got written here is dy dx. So what this means, if we wanted to give a name for this or explain it in terms of real world things, what this is, it gives the rate of change, in y with respect, let's fix that up, to x. So what this was really saying is, how much is y changing, or what is the rate of change of y as x changes? So the rate, how does y change as x changes? So we might see a couple of other examples where we've got, might have dh dt, which might be the variation of height of something, or the rate of height, or change in the height as time. We might have, what's another one, dc dt, which might be the rate of change of some sort of capacity or count. This tends to get used a bit when we're looking at radioactivity of materials. So how many counts per second are there in terms of time? So it could also be something like change in velocity over time, or if we take height, we could be measuring height in meters and time in seconds. So the units for this would actually be meters per second. So you can see that h is in m, t is in seconds, so height as meters per second. So let's go through and look at an example and see how this applies into a real world situation. So I'm just going through example 13 from the textbook, which says, according to a psychologist, the ability of a child's understanding spatial concepts is given by this formula: A is equal to a third root t, where t is in years, t is equal to age in years, and for this it's between the ages of 5 and 18. And what we've got to find is the rate of improvement in ability to understand spatial concepts when the child is 9 and 16. So in order to find out the rate of change of their understanding, we need to first find the derivative of this. So let's do that first. What this is going to be a third times x to the power of a half. And we know that the derivative of this, when we work it out, is going to be a third times a half to the power of x minus a half. And this will be equal to 1 over 6 root t. Now the reason it's root t because we've got our inverse here and it's going to be pushed down. Okay, so now what we're going to do is plug in the values of, so we need to find out rate of improvement, rate of when t is equal to 9. I'll do that one first. So we're going to have 1 divided by 6 to square root 9. And this is going to be 1 divided by square root of 9 is 3. 3 times 6 is just 18. And what about if we go when t is equal to 16? Again, 16 is still a square number, so it's going to make it nice and easy for us. So we're going to have 1 over 6 root 16, which we know is 4. So 1 divided by 4 times 6, 24. And we can see that the rate of change is decreasing. So what we need to do then, the next part of this question, so we've got our rate of improvement for is 1 over 24 units per year for a 16-year-old child and 1 over 18 per year for a 9-year-old child. What we're going to look at is, the next question is, show that dA dt is greater than 0 for between the 5 and 18. So if we have a look, our square root t can never be negative, so t always has to be positive. We can't have, there's no other negative number that can be in here, so it always has to be positive. So hopefully that's pretty easy to understand. If t is 0, then it's just going to be 1 over 6. If t is 1, again, it's 1 over 6, 2, and it will slowly start to decrease and decrease and decrease. So t can never be negative, and especially when we're dealing with anything that's got time in it, 99.999% of the time, t will never be negative. So we might want to see what's going on just before time equals 0, if there is anything, but more often than not, t, if it's time, will never be negative. So in that case, this has always got to be greater than 0. Alright, so the next question asks to show that d squared a over dt squared is less than 0 for this age range that we've got here. It's worth noting we should use this kind of notation for our rates of change. So let's rewrite this as dA dt. So we've got dA over dt is equal to 1 over 6 root t, which is also equal to 1 over 6 t to the power of minus a half. Alright, so we asked to find our second derivative, which is written as d squared a over dt squared. Alright, so let's take our half out the front. So we've got minus a half times 1 over 6 t to the power of minus 3 on 2. All of this is going to equal minus a half times 6 is just 1 over 12. Or what should I say? Minus 1 over 12. T to the power of minus 3 on 2, which is all equal to minus 1 over 12 t root t. So we know that anything, if it's minus, say t to the power of minus 3 on 2, x to the power of minus 3 on 2 is just, or even if it's to the power of 3 on 2, it's t root t. If you think about it, remember our indices laws say that if we multiply two numbers that have powers together, we add them together. So we've got a whole here that we can take out, which is 2 on 2, which leaves us with 1 on 2, which gives us this. Alright, so if we have a look here, we've got this minus sign out the front. It doesn't matter what the value of t is. It can be, in this case, it needs to be greater than 0, because we've still got this square root t, so t has to be greater than or equal to 0. Or actually, even in this case, it has to be greater than 0. It can't be equal to 0, because otherwise we've got 1 divided by, or negative 1 divided by 0. We can't divide by 0. So t has to be greater than 0. And even when it's greater than 0, it doesn't matter what number it is, we've still got this minus sign out the front. So therefore, for all of our range here between 5 and 18, this is going to be negative. Doesn't matter what number you plug in here, it's going to be negative, because we have this minus sign out the front, and we cannot be less than 0. So I hope this example makes sense. What this is also going to say is that while the ability to understand spatial concepts increases with age, the rate of increase slows down with age. So our ability to understand increases, the rate in which we understand decreases as well. Hopefully that makes a bit of sense, and if you have any questions, come and ask. Thanks for watching.